Hey everyone, it's time for physics today. Light is an oscillating electric and magnetic field. Here's a simplified diagram of a light wave. Notice how the wave is moving to the right, but the oscillations of the electric and magnetic field are perpendicular to the wave's motion. This is why light is a transverse wave. We'll talk about electric and magnetic fields in later units. Like I said before, though, this is a simplified diagram, and light that we get from the sun or a light bulb doesn't look like that at all. And in reality, there's an electric field and a magnetic field oscillating in all directions. But there's a way that we can make light look like this. We can polarize it. So like I said, the light that we get from the sun or light bulb is what is called unpolarized light. And what this means is that the electric and magnetic fields are oscillating in every single direction. Here I've only drawn the electric fields for simplicity. But by polarizing the light, we can kind of tame the light and only make it go in a single direction. We can filter out all of the other directions. So if we take unpolarized light and we shine it through a polarizer, we see that all that happens is that the intensity of the light decreases by a little bit. But if I attempt to polarize this polarized light again, there is a certain angle that it can hold the second polarizing lens where the light will completely cancel out. The light will disappear. So there we had some unpolarized light shining through a polarizer. Polarizers have a certain polarization axis. In this case, it's going to be 0 degrees from the horizontal. When the light makes it through this polarizing filter, the light that comes out the other side is in fact polarized. So maybe over here we have an initial intensity of I0, and over here we have another intensity of, let's say, I1. Now if we take this polarized light and we shine it through another polarizer, but let's say the polarizing axis is now 90 degrees to whatever that polarized light was, 90 degrees. What results over here is no light, no intensity of light. And we can call that perhaps I2, which would equal 0. The light from your computer screen is already polarized, so we really only need one lens to completely cancel out the light. But if we do have two lenses, it can create some pretty interesting results as well. But what about the intermediate angles? The angles between 0 degrees and 90 degrees? We've observed that the intensity of light that passes through a polarizing filter is dependent on what orientation or angle that polarizer is at. So right now, most of that light is getting through, but if I spin it, none of that light is getting through. But if I go maybe halfway, we can see that some of that light is getting through. There's an equation that describes polarizers called the law of Malice, and it goes like this. Some intensity after a polarizer, let's say over there, is equal to the intensity of the light that came before that polarizer. I'll call it I(n minus 1) times the cosine squared of phi. That's another Greek letter, phi. And what phi means is the difference in angle. The difference in angle. This will make more sense once we do an example here. But also remember, this equation only works if the light is already polarized. So let's do an example here. Let's say we have some unpolarized light coming in here into our polarizing filter, and let's say that that polarizing filter is tilted. It's going to be tilted at an angle of, let's say, 15 degrees. So this theta 1 here, we'll call it, is 15 degrees. So remember that, and also we have an intensity here of I naught. But remember that this equation only works for light that is already polarized. Remember that this is unpolarized over here. So if we have unpolarized light getting filtered through a polarizer, the intensity that comes out of the other side is always going to be 1/2 of the original intensity. Let me say that again. If we have unpolarized light going through a polarizer, the intensity, the new intensity coming out on this side, is going to be exactly 1/2 of that original intensity. So if I naught over here, let's say, was 30 watts per meter squared, then over here our new intensity, our new polarized light, is going to have an intensity of 15 watts per meter squared. But now let's say we want to polarize that light. We want to polarize the already polarized light. And let's say we're going to orient this polarizer at an angle of 90 degrees. Here theta is 90 degrees. Well, the light that's going to go through there is going to be polarized 90 degrees. But now, because this light is already polarized, we can use this equation. So we're going to get I2. Here we have a new intensity. Here was I1. Here was I naught, I1. Now here we have I2. It's going to be the initial, or it's going to be the intensity that came before it, that n-1. So 2 minus 1 is 1. Here's I1 times the cosine squared of phi. Now let's start plugging some numbers here. We have I2 is equal to I1, which was 15 watts per meter squared, times the cosine squared of phi. Remember, phi was the difference in angle. It's not going to be 90 degrees. It's going to be 90 minus 15 degrees. And if we go into our calculator here, what we can type in, we can do the cosine first. So cosine of 90 minus 15, or 75. And then, but that's cosine squared, so we have to square that answer. And then, of course, we multiply it by 15, and we get that I2 is equal to 1.00 watts per meter squared.